Somewhere in the darkness of space, a star explodes, a violent supernova that should destroy the star forever. For most stars, that is the end. The light fades, the star dies, but sometimes something impossible happens. The dead star refuses to disappear. Instead, it begins stealing matter from a nearby star, slowly rebuilding itself after its own destruction. Astronomers call these objects zombie stars, stars that should be dead, yet somehow continue to burn. But how can a star survive its own explosion? Tonight, we explore one of the strangest mysteries in the universe. Before we begin, subscribe to Stellar Depth as we continue exploring the most mysterious objects in the cosmos. The stars that refuse to die. For as long as humanity has looked up at the night sky, stars have seemed eternal. They rise each evening, they shine through the darkness, and they appear unchanged for countless generations. But in reality, stars live complicated lives. They are born, they grow, they age, and eventually, they die. Every star in the universe follows this fundamental cycle. Some live for only a few million years, others survive for billions. But no star escapes the final stage of its existence: stellar death. When a star finally exhausts the fuel in its core, the delicate balance that held it together begins to collapse. For millions or billions of years, the star had maintained a perfect equilibrium. Gravity pulled inward. Nuclear fusion pushed outward. These two forces fought endlessly, creating the brilliant light we see from Earth. But when the nuclear fuel runs out, the battle ends. Gravity wins, the core collapses, the outer layers are violently expelled into space, and the star reaches the end of its life. Sometimes this ending is quiet, a gentle fading of light as the star shrinks into a dense white dwarf. Other times, however, the death of a star is anything but peaceful. In the most dramatic cases, the star explodes in one of the most powerful events in the universe, a supernova. For a brief moment, the dying star can shine brighter than an entire galaxy. Energy equivalent to billions of suns is released in a single catastrophic burst. Shock waves race across space. Stellar material is hurled outward at thousands of kilometers per second. The explosion tears the star apart, or at least, that is what we once believed. For decades, astronomers assumed that when a star exploded as a supernova, the story ended there. The star was destroyed, its remains scattered across the cosmos. Another chapter closed in the endless cycle of stellar life. But modern observations have revealed something far stranger. In some rare cases, the star does not completely disappear. Something survives, hidden within the expanding debris of the explosion, a dense stellar remnant, damaged, changed, but not entirely gone. These remnants are some of the most extreme objects in existence. White dwarfs, neutron stars, collapsed cores with densities so high that a teaspoon of their material could weigh billions of tons. Under normal circumstances, these remnants slowly cool over time. They fade into darkness, their energy gradually dissipating across millions or billions of years. Yet, in certain unusual star systems, the story takes a different path. A path that leads to one of the strangest phenomena astronomers have ever observed. Zombie stars. Stars that should have died in their own explosions, but somehow continue to exist. The key to understanding these strange objects lies in the fact that most stars in our galaxy are not alone. In fact, The majority of stars exist in pairs, binary systems. Two stars bound together by gravity, orbiting a common center. These stellar partners can influence each other in profound ways, especially when one of them begins to die. Imagine two stars locked in a slow gravitational dance. For millions or billions of years, they orbit peacefully, but eventually, one of them evolves faster. It ages, its core becomes unstable, and the star expands into a massive red giant. As it swells outward, its outer atmosphere can stretch so far that it begins to drift toward its companion. Gas flows from one star to the other, a steady stream of stellar material crossing the empty space between them. If the receiving star happens to be a white dwarf, the dense corpse of a once normal star, something extraordinary can occur. White dwarfs are incredibly compact. They contain roughly the mass of the Sun, compressed into a sphere about the size of Earth. Their gravity is intense. When gas from the companion star falls onto their surface, it is compressed under enormous pressure. Temperatures rapidly rise. Hydrogen accumulates in a thin layer, and eventually, that layer ignites. In a sudden burst of nuclear fusion, this explosion is known as a nova. For a brief time, the white dwarf dramatically brightens. Astronomers observing from Earth suddenly see a star that was previously faint erupt into brilliance. But unlike a supernova, a nova does not destroy the star. The explosion only affects the thin surface layer of gas. The white dwarf itself remains intact. After the blast, the system slowly settles down again. But the process can repeat, again and again. Each cycle adds new fuel. Each eruption blasts some material back into space, and each time, the white dwarf survives. This is where the strange concept of zombie stars begins to emerge, because in some extraordinary cases, the original supernova that created the white dwarf did not fully destroy the star. Instead, the explosion was weaker than expected. Astronomers called these events failed supernovae or partial supernovae. The star begins to explode, but the blast is not strong enough to completely tear it apart. Part of the star survives, a shattered core, a wounded remnant, still orbiting its companion star. And if conditions are right, this remnant can begin feeding on its neighbor, pulling gas from the companion, rebuilding itself slowly over time, like a cosmic creature clawing its way back from the grave. These are the objects scientists refer to as zombie stars. They are not truly alive, but they are not entirely dead either. They are stellar corpses that refuse to fade quietly into darkness. Instead, they continue interacting with their surroundings, accreting matter, producing bursts of energy, sometimes even triggering new explosions. The discovery of these strange stars has forced astronomers to rethink how stellar explosions actually work. For decades, supernovae were considered clean endings. A star either exploded completely or collapsed into a neutron star or black hole. But zombie stars reveal that the universe is far more complicated. Not every stellar death is final. Some stars linger, damaged but persistent, caught between destruction and survival. And the deeper astronomers look into our galaxy, the more evidence they find that these cosmic undead may be more common than we once imagined. Some zombie stars hide in binary systems, others wander quietly through space, their violent past almost invisible. But occasionally, one reveals itself, through strange bursts of light, unusual chemical signatures, or unexpected behavior that cannot be explained by ordinary stellar physics. Each new observation raises more questions. How many of these stars exist? How long can they survive after their supposed death? And could some of them eventually explode again in an even more catastrophic event? To answer these questions, astronomers have begun searching the skies for the fingerprints of these mysterious objects, using powerful telescopes on Earth and in space, observing the faint glow of distant galaxies, and studying the aftermath of stellar explosions in unprecedented detail. What they are discovering is reshaping our understanding of how stars live and how they die. Because in the strange and violent universe we inhabit, death is not always the end, and sometimes a star that should have vanished forever comes back, not fully alive, but not entirely gone either. A silent reminder that even the most powerful explosions in the cosmos do not always finish what they begin. When a star refuses to disappear, for a long time, astronomers believed they understood how stars die. The process seemed simple. A star burns its nuclear fuel for millions or billions of years. Eventually, that fuel runs out. Gravity takes control, and the star collapses or explodes. The final outcome depends on the star's mass. Small stars like our Sun die quietly. They expand into red giants. Their outer layers drift into space, forming glowing clouds called planetary nebulae. At the center, a tiny remnant remains, a white dwarf, dense, hot, but slowly cooling over time. Massive stars, however, meet a far more violent end. When their nuclear fuel is exhausted, their cores collapse in seconds. The outer layers rebound in an enormous explosion. A supernova. For a brief moment, the dying star can shine brighter than billions of suns. The explosion tears the star apart, or at least, that is what astronomers once assumed. But as telescopes became more powerful, something unusual began to appear in the data. Some supernovae did not behave the way scientists expected. The explosions seemed weaker, less energetic. Instead of completely destroying the star, something appeared to survive. At first, researchers thought these strange observations were mistakes. Perhaps the measurements were wrong. Perhaps the explosion simply hadn't been observed clearly. But over time, more examples appeared, and a pattern began to emerge. Some stars were exploding without fully dying. These events are now known as Type 1ax supernova, a rare and unusual class of stellar explosions. Unlike typical supernovae, which completely obliterate the star, Type 1ax explosions are weaker. The blast partially disrupts the star, but the core can survive. Imagine a powerful explosion tearing apart most of a star's outer layers, debris racing outward into space, shockwaves expanding for billions of kilometers. Yet deep inside the chaos, a portion of the star remains intact, a damaged core, a stellar remnant that continues to exist. This is the birth of a zombie star, a star that should have been destroyed, but somehow survives the catastrophe. One of the most famous examples of this phenomenon was discovered in a galaxy about 110 million light-years away. Astronomers were studying the remnants of a strange supernova known as SN2012Z. The explosion had been observed years earlier, but when scientists later examined the location using the Hubble Space Telescope, they noticed something surprising. The star had not completely disappeared. Instead of fading into nothingness, a faint object still remained. Even more strangely, this surviving object appeared brighter than the original star. Something had changed. The explosion had not destroyed the star. It had transformed it. Researchers believe that during the explosion, a portion of the star's material was blasted outward, but the core survived. Now heated and disturbed by the violent event, the remaining star began expanding again, becoming hotter and brighter than before. A wounded survivor of its own death, this discovery provided some of the strongest evidence yet that zombie stars truly exist. But it also raised a new mystery. Why do some stars explode completely, while others survive? The answer may lie in the delicate physics of white dwarfs. White dwarfs are the dense remnants of stars that once resembled our Sun. Although they are small, roughly the size of Earth, they contain enormous mass. Gravity on their surface is extremely strong, and the matter inside them behaves in unusual ways. Instead of ordinary atoms, white dwarfs are supported by something called electron degeneracy pressure, a quantum mechanical effect that prevents the star from collapsing further. But this strange state of matter has limits. If a white dwarf becomes too massive, the pressure can no longer support it. The star becomes unstable. The critical threshold is known as the Chandrasekhar limit, about 1.4 times the mass of the Sun. If a white dwarf exceeds this limit, the star collapses catastrophically, triggering a massive thermonuclear explosion. This type of explosion is known as a Type 1a supernova. In most cases, the explosion completely destroys the star. But if the conditions are slightly different, something remarkable can happen. Instead of triggering a full thermonuclear detonation, the burning begins more slowly. A weaker flame spreads through the star. Astronomers call this a deflagration. Unlike a detonation, which travels faster than the speed of sound, a deflagration moves more slowly. The explosion becomes uneven, chaotic, and in some cases, insufficient to destroy the entire star. The blast tears away much of the outer layers, but the core survives, a stellar corpse left behind after a failed explosion. And if this remnant still exists within a binary system, the story is far from over, because the companion star continues orbiting nearby, and gravity continues pulling matter from one star to the other. Gas slowly flows toward the damaged white dwarf, accumulating on its surface, layer by layer. Over time, the star begins to grow again, rebuilding itself, almost like a creature regenerating after a devastating injury. This strange process turns the surviving remnant into something truly extraordinary. A star that died, but refuses to remain dead. Each new burst of nuclear burning adds energy. Each nova eruption reshapes the star. And slowly, the object evolves into something astronomers are only beginning to understand. Zombie stars may continue feeding on their companion stars for millions of years, growing heavier, hotter, more unstable. Eventually, the star might cross the Chandrasekhar limit again, but this time, the explosion could be far more powerful, a second attempt at destruction. And perhaps this time, the star will not survive. But until that moment arrives, the zombie star persists, haunting the galaxy like the ghost of a once normal star. Astronomers suspect there may be many such objects scattered throughout the Milky Way, some hidden within binary star systems, others drifting quietly through space, their violent past nearly impossible to detect, but occasionally a strange flicker of light, an unusual burst of radiation, or a faint surviving remnant after a supernova reveals their presence. Each discovery pushes the boundaries of our understanding, because zombie stars challenge one of the most basic assumptions in astronomy, that when a star explodes, it dies. But the universe has a way of defying simple rules, and in the vast darkness between the stars, some of the dead are not entirely gone. Instead, they linger, burning faintly, feeding on nearby stars, waiting for the next explosion that may finally end their strange existence. Feeding on a companion star. To truly understand how zombie stars survive, we must look more closely at the environment where they are born, because most of these strange objects do not exist alone. They are part of binary systems. Two stars locked together by gravity, orbiting each other for millions or even billions of years. At first, the relationship between these two stars may appear peaceful. They circle one another slowly through the galaxy, each star evolving at its own pace. But over time, their lives become deeply intertwined, especially when one of the stars begins to die. Stars with slightly greater mass evolve faster. Their cores burn hotter. Their nuclear fuel is consumed more quickly. Eventually, the star begins to expand. Its outer layers swell outward, transforming it into a red giant. This stage of stellar evolution is enormous in scale. A star that once resembled the Sun can expand hundreds of times larger, its atmosphere becoming thin and extended. If a companion star orbits nearby, the expanding red giant can reach a critical boundary, a region known as the Roche lobe. This invisible gravitational boundary defines the region where material remains gravitationally bound to the star. But once the star expands beyond this boundary, something remarkable happens. Gas begins to spill outward, not randomly, but in a steady stream flowing toward the companion star. Astronomers call this process mass transfer. Material from one star slowly falling onto the other. If the receiving star happens to be a white dwarf, the dense remnant of a dead star, this process can produce dramatic consequences. The white dwarf's gravity is incredibly strong. As gas from the companion star approaches, it does not fall directly onto the surface. Instead, the gas begins to spiral inward, forming a glowing disk around the white dwarf. This structure is known as an accretion disk. Within this disk, matter races around the star at tremendous speeds. Friction heats the gas to extreme temperatures. The disk begins to glow brightly, often producing intense radiation across many wavelengths of light. X-rays, ultraviolet light, visible light, all generated by the violent motion of gas spiraling toward the star. Eventually, the material in the accretion disk slowly drifts inward, falling onto the surface of the white dwarf. But the white dwarf is unlike any ordinary star. Its gravity compresses the incoming gas to incredible densities. Hydrogen accumulates in a thin layer. Pressure rises, temperature climbs, and eventually, the conditions become perfect for nuclear fusion. But this fusion does not happen deep inside the star. It occurs right on the surface. When enough hydrogen builds up, it suddenly ignites in a violent thermonuclear flash. This eruption is known as a nova. For a brief moment, the white dwarf becomes dramatically brighter. Astronomers observing from Earth see what appears to be a new star suddenly appearing in the sky. This is actually where the word nova comes from, the Latin word for new. But the star itself is not new. It is a dead star experiencing a sudden burst of nuclear burning. The explosion blasts the accumulated hydrogen back into space. Gas clouds expand outward at thousands of kilometers per second. The brightness fades again within weeks or months, and the system slowly returns to normal. But the white dwarf itself survives, unharmed, still orbiting its companion star, still pulling gas from its neighbor. Over time, the cycle begins again. Gas accumulates, pressure builds, fusion ignites, another nova erupts. Some systems repeat this process many times. These are known as recurrent novae, explosions that occur every few decades or every few centuries. Each eruption ejects material into space, but the white dwarf remains, quietly rebuilding its fuel supply once more. Now, imagine a white dwarf that has already survived a partial supernova, a damaged stellar remnant, a zombie star. This object may still exist within a binary system, still close to its companion star, still capable of stealing gas through mass transfer. But the explosion that nearly destroyed it has changed its structure. The interior of the star may be unstable, its surface temperature unusually high, its chemical composition altered by the earlier explosion. When such a star begins feeding on a companion again, the results can become even more unpredictable. Gas falling onto the star may trigger repeated nova eruptions, or it may slowly increase the star's mass, pushing it closer to the Chandrasekhar limit once again. Each new eruption reshapes the star, blasting away some material, but often allowing a portion to remain behind, gradually increasing the star's total mass, like a wounded creature slowly regenerating. In some cases, the zombie star becomes surrounded by glowing clouds of gas, remnants of past eruptions, shells of material expanding outward through space. Astronomers can detect these shells using powerful telescopes, studying the light emitted by the hot gas. By analyzing this light, scientists can determine the chemical elements present within the cloud: carbon, oxygen, iron. Heavy elements forged during nuclear explosions. Each shell tells a story about the violent history of the star. Multiple eruptions, repeated cycles of destruction and survival. Evidence that the star has already died once, yet somehow continues to exist. Some zombie stars may remain in this strange state for millions of years, locked in a continuous cycle of feeding and eruption. But there is always a looming danger, because every time the star gains more mass, it moves closer to a catastrophic threshold, the Chandrasekhar limit. Once that limit is crossed, the star can no longer support itself. The pressure inside the white dwarf becomes overwhelming. Nuclear reactions ignite throughout the star, and a new thermonuclear explosion begins. This time, far more powerful than the failed explosion that created the zombie star in the first place. If this explosion occurs, it will produce one of the brightest events in the universe. A Type 1. A supernova. Unlike the weaker explosions that leave remnants behind, this blast will completely destroy the star. No core, no survivor. Only expanding debris racing across the galaxy, But until that moment arrives, the zombie star continues its strange existence, feeding, erupting, rebuilding, defying the normal rules of stellar life. Astronomers believe that some of these stars may already exist within our own galaxy, hidden among billions of other stars, too faint or too distant to detect easily. Yet occasionally, telescopes capture a brief flash of light. A nova eruption, a strange spectral signature, or an unusual stellar remnant that does not fit any known model. Each observation adds another piece to the puzzle, a growing realization that the universe is filled with stars whose stories did not end when they were supposed to, stars that survived their own destruction, stars that feed on their companions to continue burning, stars that linger in a strange state between life and death. And as astronomers continue exploring the sky with ever more powerful instruments, they are discovering that these cosmic undead may be far more common than anyone once imagined. The explosion that wasn't strong enough. For most of the 20th century, astronomers believed that supernova explosions were final. When a star exploded, the story ended. The star was gone. Its matter scattered across the galaxy, and nothing remained except expanding clouds of debris. This assumption seemed reasonable. Supernovae are among the most violent events in the universe. In a matter of seconds, a star can release more energy than our sun will produce during its entire lifetime. The blast wave expands outward at incredible speeds. Shock waves sweep through space. Heavy elements forged inside the star are thrown into the surrounding interstellar medium. These elements eventually become the building blocks of new stars, planets, and even life. In many ways, supernovae are the universe's recycling engines. They destroy stars, but they also create the materials necessary for future generations of stars and planets. Yet, as telescopes improved and observations became more precise, astronomers began noticing strange exceptions. Some explosions did not look quite right. They were dimmer than expected, slower, weaker. The debris expanded differently than predicted. Instead of completely obliterating the star, something appeared to survive. At first, these unusual events confused astronomers. They did not match the known categories of stellar explosions. But as more examples were discovered, scientists realized they were observing a new kind of supernova, a failed explosion. An event where the star begins to destroy itself, but the process stops before it finishes. These events are now classified as Type 1 AX supernovae. They are sometimes described as the weaker cousins of Type 1a supernova. Both types involve white dwarf stars. Both involve thermonuclear explosions triggered when the star becomes too massive. But the difference lies in how the explosion spreads through the star. In a typical Type 1a supernova, the thermonuclear reaction ignites in the star's core. The burning front moves outward rapidly. Soon, the entire star becomes engulfed in nuclear fire. The star is completely destroyed. But in a Type 1ax explosion, the process unfolds differently. The burning begins in the core, but it spreads unevenly. Instead of a violent detonation traveling faster than sound, the flame moves more slowly. A turbulent, burning wave. This slower process is known as a deflagration. Because the flame travels more slowly, it cannot fully consume the star. Some regions of the white dwarf are burned, others remain untouched. The explosion disrupts the star, but it does not completely destroy it. Material is blasted outward into space, but the core survives. The star is left partially intact, damaged, distorted, but still existing. Imagine a bomb detonating inside a building. The blast tears away walls. Windows shatter. Debris flies outward in every direction. But somehow, the structure itself remains standing, broken, burned, but not completely destroyed. This is essentially what happens during a Type 1 AX supernova. The star survives its own explosion. And when the debris cloud slowly fades over time, a strange survivor remains behind. A zombie star. One of the most fascinating examples of this phenomenon occurred in a galaxy known as NG C1309, located roughly 100 million light-years away. In 2012, astronomers observed a supernova explosion in this galaxy. The event was labeled SN2012Z. At first, the explosion seemed unusual but not extraordinary. But years later, astronomers returned to study the same region using the Hubble Space Telescope. They expected to see nothing. After all, the star should have been destroyed. But something surprising appeared in the images. A faint object remained at the exact location where the supernova had occurred. Even more astonishing, the object appeared brighter than the original star had been before the explosion. This suggested that the explosion had not destroyed the star. Instead, it had dramatically altered it. The surviving remnant had expanded and heated up, becoming temporarily brighter than before. A wounded survivor glowing within the expanding debris of its own explosion. Further observations confirmed that the explosion had been incomplete. The star had lost a significant portion of its outer layers, but its core remained intact, a stellar corpse that refused to vanish. The discovery of SN2012Z provided powerful evidence that zombie stars are real. But it also raised deeper questions. How many stars survive these partial explosions? And what happens to them afterward? Computer simulations have provided some possible answers. When a white dwarf experiences a deflagration explosion, the burning may push large portions of the star outward. But because the explosion is uneven, gravity can pull some material back toward the core. This returning matter falls inward again, recombining with the surviving core. The star effectively rebuilds itself, but the remnant is no longer the same. Its internal structure has been disrupted, its outer layers altered, and radioactive elements created during the explosion may continue heating the star from within. This internal heating can cause the remnant to expand, making the zombie star appear larger and brighter than before. Over time, however, the star may slowly cool again, settling into a strange new equilibrium, a stellar remnant unlike any ordinary white dwarf. Astronomers believe that many zombie stars may exist throughout the universe, but detecting them is extremely difficult. Once the debris from the explosion fades away, the surviving remnant can be faint and hard to distinguish from other stars. Only careful observations can reveal the unusual chemical signatures or motion patterns that indicate a zombie star. Some of these remnants may continue interacting with companion stars, stealing matter through accretion, reigniting nuclear reactions on their surfaces. Others may wander through space alone, their violent past hidden behind a quiet exterior. But the most intriguing possibility is that some zombie stars may explode again. Because if the remnant continues gaining mass from a companion star, it could eventually approach the Chandrasekhar limit once more. And if that happens, a second explosion could occur. But this time, the explosion might be far more powerful, strong enough to destroy the star completely, or perhaps even create something more extreme, a neutron star, or in rare cases, a black hole. These possibilities are still being studied. Astronomers continue searching the skies for more examples of these strange objects. Using space telescopes, X-ray observatories, and massive ground-based instruments. Each discovery adds new pieces to the puzzle, a growing realization that the life cycles of stars are far more complex than once imagined. Not every star dies cleanly. Not every explosion finishes the job, and sometimes a star that should have vanished forever remains behind, broken, scarred by the explosion, yet still burning faintly in the darkness of space, a cosmic reminder that even the most powerful forces in the universe do not always succeed in ending a star's life. The wandering dead stars. When most people imagine zombie stars, they picture them trapped in binary systems, feeding on companion stars, stealing gas, rebuilding themselves through slow accretion. And while many zombie stars do exist in these kinds of systems, some do not. Some of them escape, drifting alone through the galaxy, quiet survivors of explosions that failed to destroy them. These are perhaps the strangest zombie stars of all, because they carry the scars of their violent past wherever they go. When a supernova occurs in a binary system, the explosion is rarely symmetrical. The blast does not expand evenly in every direction. Instead, the explosion can be lopsided, more powerful on one side, weaker on the other. This imbalance creates something astronomers call a kick, a sudden burst of momentum that sends the surviving remnant flying through space. Imagine two stars orbiting each other. One of them explodes. The blast violently disrupts the gravitational balance between them. If the explosion is uneven, the surviving remnant can be flung away at tremendous speed, sometimes hundreds of kilometers per second. In many cases, the explosion also destroys the gravitational bond between the two stars. The binary system breaks apart. The companion star continues moving along its original path, and the surviving remnant, the zombie star, is launched into the galaxy alone. Astronomers refer to these objects as runaway stars, but zombie stars can be even more extreme, because their unusual structure and explosive history leave behind detectable clues. Their motion through space is often unusually fast. Their chemical composition can reveal the nuclear reactions that took place during the partial supernova, and their temperature can be far higher than expected for normal stellar remnants. One fascinating example of such an object is a star known as LP4O-365, located roughly 2,000 light-years away from Earth. LP4O-365 is unlike almost any other star discovered. It is small, dense, and moving through space at extraordinary speed, nearly 2 million kilometers per hour. Astronomers studying this star notice something strange about its composition. Normally, white dwarfs contain large amounts of carbon and oxygen, but LP4O-365 is different. Its atmosphere contains unusual elements: neon, magnesium, oxygen, heavy materials that are typically produced during thermonuclear explosions. This strange chemistry suggests that LP4 O-365 is not an ordinary white dwarf. Instead, it appears to be the surviving remnant of a partial supernova, a zombie star, a stellar corpse that survived an explosion and was launched across the galaxy by the blast. Its incredible speed supports this idea. The force of the explosion likely acted like a cosmic cannon, firing the remnant into space at tremendous velocity. Today, LP4 O-365 continues racing through the Milky Way, a lone survivor wandering through the galaxy. But it is not alone. Astronomers have now discovered several similar objects, stars that appear to be remnants of incomplete supernova explosions, each one traveling at unusual speeds, each one carrying strange chemical fingerprints from the explosion that nearly destroyed them. These discoveries suggest that zombie stars may not always remain in binary systems. Some escape, becoming solitary travelers, ghosts of stellar explosions drifting through interstellar space. And these runaway zombie stars offer astronomers an incredible opportunity, because they allow scientists to study the aftermath of failed supernovae in ways that would otherwise be impossible. By analyzing the light coming from these stars, researchers can determine their temperature, mass, and chemical composition. Spectroscopy, the study of how matter emits and absorbs light, reveals which elements exist in the star's atmosphere. These chemical signatures act like forensic evidence, clues left behind by the nuclear reactions that took place during the explosion. For example, the presence of heavy elements such as manganese, iron, and nickel can reveal how hot the explosion became. Other elements indicate how deeply the nuclear burning penetrated into the star. Each zombie star therefore becomes a kind of cosmic crime scene, a remnant containing the clues needed to reconstruct a stellar catastrophe. And these clues are helping astronomers solve one of the biggest mysteries in modern astrophysics. How do Type 1a X supernovae actually work? These weaker explosions have puzzled scientists for decades. But by studying zombie star remnants, researchers are finally beginning to understand the physics behind them. Computer simulations now suggest that when a white dwarf undergoes a deflagration explosion, the burning flame may become chaotic. Instead of spreading evenly through the star, the flame forms turbulent plumes. These plumes burn some regions of the star while leaving others untouched. The uneven explosion ejects large amounts of material, but the remaining core can survive. The blast also pushes the remnant in one direction, creating the runaway zombie stars we observe today. Over time, these wandering remnants slowly cool. Their brightness fades. Their motion carries them farther away from the site of their original explosion. Eventually, they may travel thousands of light years across the galaxy, becoming almost impossible to trace back to their origins. But for now, a handful of these strange stars have been identified, each one providing new evidence that zombie stars are real, and that stellar explosions do not always end the life of a star. Instead, some stars survive, broken, transformed, but still existing. Their journeys across the galaxy continue long after the explosion that should have destroyed them. And somewhere out there, drifting through the dark spaces between the stars, are the silent survivors of failed supernovae, stellar corpses launched into the universe, traveling endlessly through the Milky Way, a reminder that in the cosmos, even death does not always bring an end. Sometimes, the dead stars keep moving. The second death zombie stars exist in a strange state between survival and destruction. They are stars that should have died, stars that experienced catastrophic explosions, and yet somehow they remain, damaged remnants drifting through space or feeding slowly on nearby companion stars. But their story may not end there, because the survival of a zombie star does not guarantee safety. In fact, surviving the first explosion may only delay something far worse, a second death, one that could be far more violent than the first. To understand why, we must return to one of the most important limits in astrophysics, the Chandrasekhar limit. This limit represents the maximum mass a white dwarf can have before it becomes unstable, about 1.4 times the mass of our Sun. Below this threshold, a white dwarf can remain stable for billions of years. But once the mass approaches this critical point, the star enters dangerous territory. Inside the white dwarf, gravity is pushing inward with incredible force. The star survives only because of electron degeneracy pressure, a strange quantum mechanical effect that prevents matter from collapsing further. But degeneracy pressure has limits. If the star becomes too massive, the pressure can no longer hold gravity back. The entire structure becomes unstable, and nuclear reactions ignite violently throughout the star. The result is one of the brightest explosions in the universe, a Type 1, a supernova. In most cases, this explosion completely destroys the white dwarf. Nothing remains. The star is obliterated. But zombie stars complicate this picture, because they have already experienced one failed explosion, a partial supernova that damaged the star but did not destroy it. Now, imagine what happens if that surviving remnant continues gaining mass. If the zombie star still exists in a binary system, it may continue pulling gas from its companion, slowly, patiently. Year after year, the process is gradual but relentless. Gas falls onto the surface, pressure increases, temperature rises, the star grows heavier, closer and closer to the Chandrasekhar limit, and if the zombie star eventually crosses that limit again, another explosion becomes inevitable. But this time, the explosion may be very different. The first explosion failed because the burning spread slowly through the star. A deflagration, an uneven flame that did not consume the entire star. But if conditions are slightly different during the second event, the burning could spread far more violently. A detonation, a supersonic wave of nuclear fire racing through the star. Unlike a deflagration, a detonation moves faster than the speed of sound. Once it begins, it cannot be stopped. Within seconds, the entire star becomes engulfed in nuclear fusion. The white dwarf is completely destroyed, all of its mass converted into expanding clouds of hot plasma. The explosion releases enormous energy, enough to briefly outshine an entire galaxy. Astronomers have observed these events countless times. Type 1, A, supernovae serve as important tools in cosmology because their brightness is very predictable. Scientists use them as standard candles to measure distances across the universe. In fact, these explosions helped astronomers discover that the universe is expanding faster and faster, a discovery that led to the concept of dark energy. But if zombie stars can explode again, it raises an intriguing possibility. Some of the Type 1a supernovae we observe today may actually be the second deaths of zombie stars, stars that already survived one explosion, only to face a second, final destruction later. In some cases, however, the second explosion may not occur immediately. Zombie stars can remain unstable for millions of years, slowly accreting matter, occasionally producing nova eruptions, each eruption blasting away some material, but often leaving enough behind for the star to continue growing. The balance between gaining and losing mass becomes extremely delicate. Too many eruptions may prevent the star from reaching the Chandrasekhar limit. Too much accretion may push it dangerously close to catastrophe. Astronomers are still trying to understand which systems eventually explode and which ones survive indefinitely. Computer simulations suggest that zombie stars may follow several different evolutionary paths. Some will eventually reach the Chandrasekhar limit, triggering a massive thermonuclear explosion. Others may lose mass through repeated nova eruptions, stabilizing the star and preventing a second supernova. And some may collapse into even stranger objects. If the core becomes dense enough, it could theoretically collapse further, transforming into a neutron star, an object so dense that a single teaspoon of its material would weigh billions of tons. Although this scenario is rare, it illustrates just how unpredictable the future of zombie stars can be. Each one is a ticking cosmic time bomb, a stellar remnant carrying the potential for another catastrophic event. And somewhere in our own galaxy, some of these objects may already exist, hidden within binary star systems, quietly feeding on their companions, their mass slowly increasing, their stability slowly weakening, waiting. Astronomers are actively searching for these dangerous systems, using space telescopes capable of detecting X-rays and ultraviolet radiation, because accretion disks around white dwarfs often emit powerful high-energy radiation. These signals can reveal where matter is falling onto compact stars, and which systems may eventually become unstable. Future telescopes may allow scientists to monitor these systems more closely, watching as zombie stars slowly evolve toward their ultimate fate. Perhaps one day, astronomers will observe a zombie star reaching the Chandrasekhar limit and witness the moment when its long struggle between survival and destruction finally ends. A second explosion, a final death. But until that moment arrives, these strange stellar remnants continue their uneasy existence, neither fully alive nor completely dead, burning quietly in the darkness of space. Living reminders that even the most violent explosions in the universe sometimes fail to finish their work, and that in the strange physics of the cosmos, death can arrive more than once, searching the galaxy for the undead. For centuries, humanity believed the night sky was calm and predictable. Stars appeared fixed, unchanging, permanent. But modern astronomy has revealed a very different universe, a violent universe, a place where stars are born in enormous clouds of gas, where they burn with unimaginable energy, and where they eventually die in explosions powerful enough to reshape entire regions of space. Yet among these cosmic deaths, astronomers have discovered something even more unusual: stars that refuse to disappear, zombie stars, remnants of stellar explosions that should not exist. But finding these strange objects is not easy, because after a supernova fades, the galaxy quickly hides the evidence. The expanding debris spreads out over enormous distances. The light dims. And within a few decades, the site of the explosion may appear almost normal again. Only careful observation can reveal the strange survivor left behind. This is why astronomers rely on some of the most powerful telescopes ever built. Observatories capable of detecting extremely faint light from distant stars. The Hubble Space Telescope, orbiting high above Earth's atmosphere, has played a crucial role in this search. Its ability to capture incredibly sharp images allows astronomers to compare observations taken years apart. By studying images before and after a supernova, scientists can determine whether the original star truly vanished, or whether something remained. In several cases, Hubble has revealed faint survivors glowing where a supernova once erupted. Evidence that the explosion failed to completely destroy the star. But Hubble is not alone in this search. Ground-based telescopes also play a vital role. Massive observatories such as the Very Large Telescope in Chile and the Keck Observatory in Hawaii can analyze the light from distant stars in extraordinary detail. Using a technique called spectroscopy, astronomers break starlight into its component colors. Like a rainbow produced by a prism, each element leaves a unique fingerprint within this spectrum: carbon, oxygen, iron, nickel. By examining these fingerprints, scientists can determine the chemical composition of a star. For zombie stars, this information is incredibly valuable, because their atmospheres often contain unusual elements. Evidence of nuclear reactions that occurred during the partial supernova. Some zombie stars show chemical signatures that cannot be explained by ordinary stellar evolution. Heavy elements produced only during thermonuclear explosions. These strange compositions reveal their violent past. But chemistry is only one clue. Motion is another. Some zombie stars move through the galaxy at unusually high speeds, hundreds of kilometers per second, far faster than typical stars in the Milky Way. These velocities often indicate that the star received a powerful kick during a supernova explosion. The asymmetric blast launched the remnant into space like a bullet. Astronomers can measure this motion by tracking how stars move across the sky over time. And when a star moves unusually fast, it immediately becomes a candidate for further investigation. In recent years, another powerful tool has joined the search: the Gaia Space Observatory, launched by the European Space Agency. Gaia is mapping the positions and motions of more than 1 billion stars in the Milky Way, with extraordinary precision. By tracking these stars, Gaia allows astronomers to identify objects with unusual trajectories, stars that appear to be racing through the galaxy. Some of these may be runaway stars, but others may be zombie stars, remnants of failed supernova explosions traveling through the Milky Way. Gaia's massive dataset has already revealed several mysterious, high-speed stellar remnants, objects that appear to match the predicted properties of zombie stars: small, dense, moving at incredible speeds, and carrying unusual chemical signatures. But even with these powerful tools, the search remains difficult, because zombie stars are rare. Supernova explosions themselves are relatively uncommon, and failed supernovae are even rarer. Astronomers estimate that only a small fraction of stellar explosions produce surviving remnants like these. Yet the Milky Way contains hundreds of billions of stars. Even rare phenomena can occur thousands of times across such a vast population. Some zombie stars may hide within binary systems, still feeding on companion stars. Others may wander alone through the galaxy, cooling slowly over millions of years. And some may remain invisible until their next eruption. Because zombie stars can produce occasional bursts of light, small explosions, nova eruptions. These events can briefly reveal their presence. Astronomers operating wide-field sky surveys constantly monitor the heavens for such flashes. Projects like the Zwicky Transient Facility and the Pan-STARRS survey scan large portions of the sky every night, looking for sudden changes in brightness. Transient events, short-lived phenomena that appear and disappear quickly. Many of these events turn out to be ordinary novae or supernovae, but occasionally something unusual appears. An explosion that does not behave normally. A supernova that seems too weak. Or a faint remnant glowing where the star should have disappeared. Each of these discoveries adds another piece to the puzzle, gradually revealing the hidden population of zombie stars scattered throughout the galaxy. And the search is only beginning. In the coming years, new observatories will dramatically increase our ability to detect these strange objects. One of the most anticipated is the Vera C. Rubin Observatory, currently under construction in Chile. This telescope will conduct an enormous survey of the entire southern sky, imaging the same regions repeatedly over time. Its powerful camera will detect millions of transient events, explosions, novae, and perhaps many more failed supernovae, each one providing new opportunities to identify zombie star remnants. Space-based observatories will also contribute. The James Webb Space Telescope, with its incredible sensitivity to infrared light, may be able to study the faint survivors of ancient stellar explosions, detecting remnants that are too dim for other telescopes to observe. Together, these instruments will transform our understanding of stellar death. Because for centuries, astronomers believed the life cycle of stars was simple: birth, life, death. But zombie stars reveal something far more complex. Some stars survive their own destruction. Some wander through space as the living remnants of failed explosions, and some may be quietly evolving toward an even more violent fate, hidden among the countless stars of the Milky Way, waiting to be discovered. As astronomers continue scanning the skies with ever greater precision, the number of known zombie stars will almost certainly grow, each one offering a glimpse into one of the strangest phenomena in the universe, a star that died, but somehow remained behind, a survivor of cosmic violence, and perhaps a ticking time bomb destined to explode again, a universe full of strange survivors. When astronomers first began discovering zombie stars, the idea seemed almost unbelievable. Stars that survived their own explosions, remnants left behind after a supernova that should have destroyed everything. For many scientists, it felt like discovering a ghost in the machinery of the universe. But as observations continued, something became clear. Zombie stars were not just rare accidents. They were part of a much larger story about how stars live and die. For decades, astronomers believed stellar death followed a strict set of rules. A star burns nuclear fuel. The fuel runs out. Gravity takes over, and the star collapses or explodes. Simple, predictable. But nature rarely follows perfectly simple rules. As telescopes grew more powerful, astronomers began noticing strange exceptions. Supernova explosions that were weaker than expected. Stellar remnants that should not have survived. Chemical fingerprints that did not match known models of stellar evolution. Each new discovery forced scientists to reconsider the physics of stellar death. Because the truth appears far more complex. Some stars do not explode cleanly. Instead, their explosions are chaotic, uneven, incomplete. The star begins to destroy itself, but the process fails, leaving behind a damaged survivor, and these survivors may continue evolving for millions of years after their supposed death. Zombie stars, therefore, represent something extremely important to astrophysics. They are natural laboratories, objects that allow scientists to study nuclear explosions in ways that cannot be recreated on Earth. Inside these stars, matter exists under extreme conditions, temperatures reaching hundreds of millions of degrees, pressures far greater than anything produced in human laboratories. Atoms are crushed together. Nuclear reactions occur that forge heavy elements: iron, nickel, cobalt. These elements are then blasted into space during eruptions, enriching the surrounding interstellar medium. In fact, many of the heavy elements found on Earth were created during ancient stellar explosions. The iron in your blood, the calcium in your bones, the oxygen you breathe, all forged inside stars long before the sun was born. Zombie stars therefore play a role in one of the most profound cosmic cycles, the recycling of matter. Even though their explosions may be incomplete, they still contribute elements to the galaxy. Each nova eruption ejects gas enriched by nuclear reactions. Each partial supernova spreads heavy elements into space. Over millions of years, these materials mix with interstellar clouds, eventually forming new stars, new planets, and perhaps even new life. But zombie stars may influence the universe in other ways as well. Some astronomers suspect they could help explain mysterious cosmic events. For example, certain supernova explosions appear unusually faint, too dim to match the energy expected from typical stellar explosions. These faint supernovae may actually be the explosions that create zombie stars, partial detonations that fail to destroy the star. Observing these events allows astronomers to better understand the physics of thermonuclear burning inside white dwarfs. Other researchers believe zombie stars may help explain unusual stellar remnants observed throughout the Milky Way. Stars with strange chemical compositions. Stars moving at extreme speeds. Objects that do not fit traditional models of stellar evolution. Many of these mysteries may be connected to failed supernovae, the remnants of stars that survived explosions long ago. But perhaps the most intriguing question is this: how many zombie stars exist in our galaxy? The Milky Way contains roughly 100 to 400 billion stars. Even extremely rare phenomena can occur thousands or millions of times within such a vast population. Astronomers currently estimate that Type 1a X supernovae, the explosions believed to produce zombie stars, occur about one-third as often as normal Type 1a supernova. That means failed explosions may be surprisingly common. and each of those events could leave behind a surviving remnant. If this estimate is correct, then the Milky Way could contain thousands of zombie stars, some hidden in binary systems, some wandering alone through space, and some quietly cooling after ancient explosions that occurred millions of years ago. Yet, finding them remains difficult, because zombie stars often appear faint and ordinary. Unless astronomers know exactly what to look for, these strange remnants can easily hide among the countless other stars in the galaxy. But new technology is changing that. The next generation of astronomical observatories will allow scientists to monitor the sky with unprecedented precision. Telescopes capable of detecting faint explosions in distant galaxies. Surveys that scan the entire sky repeatedly. Observatories that track the motion of millions of stars across the Milky Way. With each new observation, astronomers are uncovering more evidence that the universe is filled with strange survivors. Stars that should not exist. Stars that challenge our understanding of stellar physics. And zombie stars are only one example. Across the cosmos, astronomers have discovered many other bizarre remnants of stellar death. Neutron stars spinning hundreds of times per second. Black holes swallowing nearby stars. Magnetars with magnetic fields trillions of times stronger than Earth's. Each of these objects pushes the limits of physics, forcing scientists to develop new theories about how the universe works. But zombie stars hold a special place among these strange cosmic phenomena, because they challenge one of the most fundamental assumptions in astronomy, that when a star explodes, its story ends. Yet zombie stars prove that sometimes, even the most violent explosions in the universe are not enough. Some stars survive, scarred by the blast, altered forever, but still shining faintly in the darkness of space. And somewhere among the billions of stars in the Milky Way, these strange survivors continue their quiet existence, remnants of ancient explosions, stellar corpses that refused to disappear, silent witnesses to one of the universe's most fascinating mysteries, the possibility that in the vast cosmic cycle of birth and death, some stars simply refuse to let go. The future of zombie stars. Zombie stars may seem like strange cosmic accidents, but they could play an important role in the future of astronomy. As telescopes become more powerful, astronomers are beginning to detect more unusual stellar remnants across the Milky Way. Some of these objects move through space at incredible speeds. Others show chemical signatures that suggest they survived partial supernova explosions. Each discovery helps scientists understand how stars truly die. Future observatories, such as the Vera C. Rubin Observatory, will scan the entire sky repeatedly. This will allow astronomers to detect faint explosions and unusual stellar remnants that were previously invisible. With these new instruments, researchers expect to discover many more zombie stars hiding in our galaxy. Some may still be feeding on companion stars. Others may be drifting alone through interstellar space, and some may be slowly approaching a second, final explosion, because in the strange physics of the universe, death is not always the end. Sometimes even a star that should have vanished forever continues to shine. Stars that refuse to die. Across the vast darkness of the universe, stars are constantly being born and destroyed. Giant clouds of gas collapse under gravity. New stars ignite. They shine for millions or billions of years. and eventually they reach the end of their lives. For most stars, that ending is final, a quiet fading into darkness, or a violent supernova explosion that tears the star apart and scatters its material across space. For a long time, astronomers believed that once a star exploded, its story was over. The star was gone, its matter recycled into the galaxy, another life completed in the endless cosmic cycle. But the discovery of zombie stars has revealed something surprising. Sometimes, stellar death is not permanent. In rare cases, the explosion that should destroy a star fails to finish the job. The blast begins. Nuclear reactions ignite inside the star. Shock waves tear through its interior. Material is thrown outward into space. Yet somehow, a portion of the star survives. A dense remnant remains behind, damaged, altered, but still existing. These strange survivors are what astronomers now call zombie stars, stellar corpses that refuse to vanish after their own destruction. Some of them remain inside binary star systems, locked in orbit with a companion star, slowly pulling gas from their neighbor through powerful gravity. The stolen material spirals inward through glowing accretion disks, heating to extreme temperatures, occasionally igniting in explosive nova eruptions. Each eruption blasts gas into space, but the star itself survives, rebuilding its mass over time. Others are not so fortunate. Some zombie stars are launched across the galaxy by the force of the explosion that created them, traveling at extraordinary speeds, hundreds of kilometers per second. These runaway remnants drift through the Milky Way as lonely survivors of failed supernova. Their unusual chemical compositions reveal the nuclear reactions that nearly destroyed them, each one carrying the fingerprints of a catastrophic event. Yet despite their survival, zombie stars remain unstable. Their existence is fragile. Many of them sit dangerously close to the Chandrasekhar limit, the maximum mass a white dwarf can support before collapsing. If they continue gaining mass from companion stars, the consequences could be dramatic. The internal pressure rises, temperatures climb, and eventually, nuclear reactions ignite once more. A second explosion, this time far more powerful. One capable of destroying the star completely. But not all zombie stars will meet this fate. Some may lose mass through repeated nova eruptions, preventing them from ever reaching the critical threshold. Others may slowly cool over millions of years, fading into faint stellar remnants, their violent history hidden beneath a quiet exterior. Astronomers are still trying to understand which path these stars will follow, because zombie stars challenge many of the assumptions that scientists once held about stellar evolution. For decades, models of stellar explosions assumed that supernovae either completely destroyed stars or left behind neutron stars or black holes. But zombie stars reveal an entirely new possibility. Stars that survive. Stars that continue evolving after their supposed death. Stars that blur the boundary between life and destruction. Studying these objects has already provided valuable insights into the physics of nuclear burning inside stars. It has helped scientists refine their models of thermonuclear explosions, and it may even improve our understanding of Type 1a supernovae, some of the most important cosmic events used to measure distances across the universe. But beyond the scientific importance, zombie stars also remind us of something profound about the cosmos. the universe is far stranger than we often imagine. Even the most violent forces do not always behave as expected. Stars that should disappear sometimes remain. Explosions that should end a star's life sometimes fail. And remnants that should fade quietly into darkness can continue burning for millions of years. Somewhere in the Milky Way tonight, hidden among billions of ordinary stars, there may be zombie stars drifting silently through space, some feeding on companion stars, some racing across the galaxy as runaway remnants, and some waiting patiently for the moment when gravity and nuclear fire will once again push them toward catastrophe. Their strange existence is a reminder that in the universe, the line between life and death is not always clear. Stars may explode, they may collapse, they may fade into darkness. But sometimes, a star that should have died long ago continues to shine. A silent survivor of cosmic violence, a remnant of a failed explosion. A star that refuses to disappear. A true zombie star wandering through the endless night of space. The quiet survivors of the cosmos. In the immense silence of the universe, countless stars are living out their final moments. Some collapse into dense neutron stars. Some vanish behind the event horizons of black holes. Others explode violently, scattering their material across space in brilliant supernova explosions. For most stars, death is sudden and final. The explosion destroys everything that once held the star together. Nothing remains but expanding clouds of gas drifting through the galaxy. But zombie stars remind us that the universe rarely follows simple rules. Sometimes the explosion fails. Sometimes the star survives. Broken, scarred by the blast, but still existing. These strange survivors are among the most fascinating objects astronomers have ever discovered, because they challenge one of the most fundamental ideas about how stars die. For decades, stellar evolution seemed predictable. A star forms from collapsing gas. It shines for millions or billions of years. Eventually, its nuclear fuel runs out. Gravity overwhelms the core, and the star collapses or explodes. The cycle appeared complete. But zombie stars show that even the most powerful stellar explosions can leave something behind, a remnant that continues its existence long after it should have disappeared. Some zombie stars remain locked in binary systems. They orbit close to companion stars, slowly stealing gas from their neighbors. The stolen material spirals inward through glowing accretion disks, heating to millions of degrees, occasionally triggering nova eruptions that blast gas back into space. Yet the star itself remains intact, growing slowly heavier over time. Others are thrown across the galaxy by the explosion that nearly destroyed them. These runaway remnants travel at enormous speeds through interstellar space. Their unusual chemical compositions reveal the violent nuclear reactions that once occurred inside them. Each zombie star carries the memory of a catastrophic event, a supernova that almost ended its life. But these stars are not stable forever. Their existence is temporary. Many sit dangerously close to the Chandrasekhar limit, the critical mass where a white dwarf can no longer support itself against gravity. If they continue gaining mass from companion stars, their fate may be sealed. The pressure inside the star will rise, temperatures will increase, and nuclear fusion will ignite once again. But this time, the explosion may be unstoppable, a full thermonuclear detonation racing through the star. destroying it completely. Yet not all zombie stars will meet such a violent end. Some may slowly cool over millions of years, their brightness fading, their nuclear activity gradually slowing. Eventually, they may become faint stellar remnants, quiet relics of ancient explosions, almost impossible to distinguish from ordinary white dwarfs. But their strange origins remain hidden within their chemical structure, encoded in the elements forged during the failed supernova. Astronomers continue searching for these objects throughout the Milky Way. Each new discovery expands our understanding of stellar physics, because zombie stars represent a missing chapter in the story of how stars evolve. They reveal that stellar death is not always instantaneous. Sometimes it is a prolonged process, a struggle between gravity, nuclear reactions, and explosive forces. A star may attempt to destroy itself, but fail, leaving behind a remnant that continues evolving long after the explosion. This discovery has forced scientists to revise many models of stellar explosions. The physics of thermonuclear burning inside white dwarfs is more complicated than previously believed. Flames can spread unevenly, explosions can stall, and stars can survive events that should have completely destroyed them. Future observatories will likely reveal many more examples of these strange stellar remnants. The Vera C. Rubin Observatory will monitor the sky for faint explosions and unusual stellar activity. The James Webb Space Telescope will study distant remnants in unprecedented detail. Together, these instruments will allow astronomers to track the full life cycle of stars with greater precision than ever before. And somewhere within the billions of stars that fill our galaxy, zombie stars are quietly drifting through space. Some hidden in binary systems, some racing across the Milky Way after ancient explosions, some waiting for a second, final supernova. Their existence reminds us that the universe is not always predictable. Even the most powerful explosions do not always succeed. Even death itself can sometimes be incomplete. In the darkness between the stars, remnants of failed supernova continue their silent journeys. Stellar corpses that refused to disappear. Ghosts of ancient explosions wandering through the galaxy. And perhaps millions of years from now, some of these strange survivors will finally meet their true end. A second explosion. A final burst of light. The last moment in the long and unusual life of a star that once refused to die. The stars that challenged our understanding. For centuries, humanity believed that the universe followed simple rules. Stars were born, they lived brilliant lives, and eventually they died. The process seemed orderly, predictable, a cosmic cycle repeating endlessly across the galaxy. But modern astronomy has shown us that the universe is far more complicated. Sometimes the rules break. Sometimes the expected ending never comes. Zombie stars are one of the clearest examples of this strange reality. They are stars that should not exist. Stars that experienced violent explosions. Stars that should have vanished forever. And yet somehow they remain. The discovery of these objects has forced astronomers to rethink one of the most fundamental questions in astrophysics. What truly happens when a star dies? For decades, scientists believed they understood supernova explosions in great detail. The models were elegant. A white dwarf star slowly gains mass from a companion. Eventually, it reaches the Chandrasekhar limit. Nuclear reactions ignite, and the star explodes completely. The explosion leaves nothing behind, just expanding clouds of hot gas spreading through space. But zombie stars revealed a flaw in that assumption, because in some cases, the explosion fails. Instead of a perfect detonation, the burning spreads unevenly. A turbulent deflagration wave moves through the star, consuming some regions, skipping others. The explosion becomes chaotic, and when the energy fades, part of the star survives. A remnant left behind after a failed supernova. At first, many astronomers were skeptical. The idea seemed unlikely. Supernova explosions release enormous amounts of energy. How could anything survive such violence? But observations continued to accumulate. Strange stellar remnants began appearing in telescope data. Stars with unusual chemical compositions. Stars moving through the galaxy at incredible speeds. Stars located at the exact positions where faint supernova explosions had previously occurred. Each new discovery strengthened the case. Zombie stars were real. They were not theoretical curiosities. They were actual objects scattered throughout the galaxy. And once astronomers accepted their existence, new questions began to emerge. How common are these strange survivors? Do they exist only in rare binary systems? Or could they be far more widespread than we once imagined? To answer these questions, scientists began developing advanced computer simulations of stellar explosions. Using powerful supercomputers, researchers recreated the physics of white dwarf stars approaching the Chandrasekhar limit. They simulated thermonuclear burning waves moving through the star. And what they found was surprising. Under certain conditions, the explosion does not propagate evenly. Instead, the burning front becomes turbulent. Rising plumes of nuclear fire move through the star like boiling bubbles. These plumes burn some regions intensely, but leave others untouched. The explosion ejects large amounts of material. Yet the star's core can survive. This theoretical prediction matched the observations of zombie star remnants, and suddenly, the idea of failed supernova began to make sense. The universe was not breaking the laws of physics. It was simply revealing a more complicated version of them. Zombie stars are therefore not anomalies. They are natural outcomes of chaotic stellar explosions, and their existence opens a new window into understanding how stars behave under extreme conditions. Because the physics inside a white dwarf approaching thermonuclear explosion is incredibly complex. Temperatures exceed hundreds of millions of degrees. Nuclear reactions occur on microscopic scales, yet they influence structures thousands of kilometers wide. Small changes in density or temperature can drastically alter how the explosion unfolds. This sensitivity means that no two stellar explosions are exactly alike. Some detonate completely, others partially disrupt the star, and a few leave behind strange survivors, zombie stars, remnants of explosions that almost succeeded, but not quite. These discoveries are also important for understanding the larger structure of the universe. Type 1. A. Supernovae are used as cosmic distance markers because they reach nearly identical brightness levels during their explosions. Astronomers measure how bright these explosions appear from Earth, then calculate how far away they must be. This technique helped reveal one of the most astonishing discoveries in modern cosmology: that the expansion of the universe is accelerating, a phenomenon attributed to something called dark energy. But if some supernova explosions are incomplete, then astronomers must carefully distinguish between different types of explosions. Understanding zombie stars therefore helps improve the accuracy of cosmic distance measurements. Even small differences in brightness can influence our estimates of how fast the universe is expanding. So these strange stellar survivors are not just curiosities. They are key pieces in the puzzle of cosmic evolution. But beyond their scientific importance, zombie stars also offer something else, a reminder of the universe's unpredictability. Nature rarely behaves exactly the way we expect. Even in the immense scales of astrophysics, where gravity and nuclear reactions dominate, chaos can still play a role. A star can attempt to destroy itself and fail, leaving behind a remnant that continues drifting through space, millions of years after its supposed death. Some of these remnants may continue interacting with companion stars, feeding on nearby gas, growing slowly heavier. Others may wander through the galaxy alone, traveling thousands of light years away from the site of their original explosion. And some may eventually reach a second catastrophic moment, when their mass becomes unstable again, triggering another thermonuclear explosion, a final attempt at destruction. But until that moment arrives, zombie stars continue their strange existence, neither fully alive nor completely dead, silent witnesses to the violent processes that shape our universe, hidden among billions of ordinary stars, faint, distant, yet carrying within them the evidence of one of the most extraordinary phenomena in astrophysics, a star that died but somehow refused to disappear, a survivor of cosmic catastrophe, a wandering remnant of a failed supernova, a true zombie star, when the universe refuses to end the story. In the grand story of the universe, stars are often described as having clear beginnings and clear endings. They are born from vast clouds of gas and dust. Gravity pulls those clouds together until the pressure becomes so intense that nuclear fusion ignites. A star is born. For millions or even billions of years, that a star shines steadily, balancing gravity pulling inward and nuclear energy pushing outward. Eventually, however, the fuel that powers the star begins to run out. The delicate balance collapses, and the star enters its final chapter. For many stars, this ending is quiet. They expand into red giants. Their outer layers drift away into space, leaving behind small, dense white dwarfs that slowly cool for billions of years. But for other stars, the ending is violent. Massive stars collapse under their own gravity, their cores implode, and then rebound in enormous supernova explosions. These explosions are among the most powerful events in the cosmos. For a short time, a single exploding star can shine brighter than an entire galaxy. The blast wave spreads outward at incredible speeds. Stellar material is thrown across interstellar space. New elements forged in the explosion enrich the surrounding gas. This material eventually forms new stars, new planets, and perhaps new life. For a long time, astronomers believed that once a supernova occurred, the star was gone forever. But zombie stars have revealed a deeper truth. Sometimes the explosion fails. Sometimes the star survives. And that survival tells us something remarkable about the universe. Even the most powerful forces do not always finish what they begin. the discovery of zombie stars has reshaped how astronomers think about stellar death. It has shown that thermonuclear explosions can behave unpredictably. Small differences in temperature, density, or turbulence inside a star can determine whether it is completely destroyed or partially survives. The difference between total destruction and survival may depend on tiny fluctuations deep inside the star's core. This chaotic behavior makes the universe far more interesting than simple models once suggested. It means that stellar evolution is not always a straight path. Some stars attempt to die more than once. Some survive explosions that should have ended their existence, and some continue wandering through the galaxy as remnants of cosmic accidents. Yet even zombie stars cannot escape the long-term forces shaping the universe. Gravity continues to act upon them. Energy continues to radiate away. Their internal structure slowly evolves over time. Some zombie stars may eventually gain enough mass to trigger a second thermonuclear explosion, a final supernova powerful enough to destroy the star completely. Others may slowly cool, their nuclear reactions fading, their brightness diminishing over millions or billions of years, eventually becoming faint white dwarfs barely distinguishable from other stellar remnants, their violent history hidden beneath a quiet exterior. But even when they fade, the story they carry remains important, because zombie stars reveal how complex the universe truly is. They show that cosmic events rarely follow perfect scripts. Even when the physics is well understood, the outcome can still surprise us. And this unpredictability is part of what makes astronomy so fascinating. Each observation of the sky has the potential to reveal something unexpected. A star that behaves differently, an explosion that unfolds in a new way, a remnant that challenges our assumptions. Zombie stars are one of those discoveries, objects that forced astronomers to rethink long-held ideas about how stars end their lives. And they remind us of something profound. The universe is not static. It is dynamic, violent, creative, and sometimes strange beyond imagination. Across the Milky Way, billions of stars are currently living out their lives. Some are being born within glowing nebulae. Some are aging slowly, like our sun. And somewhere among them, hidden in the vast darkness between stars, are the quiet survivors of failed supernovae, zombie stars, stars that once tried to destroy themselves, stars that nearly vanished in cosmic explosions, but somehow, against all expectations, remained. And as astronomers continue exploring the universe with ever more powerful telescopes, they will undoubtedly discover more of these strange objects, each one carrying the memory of a failed stellar death, each one reminding us that even in the vast machinery of the cosmos, sometimes the story does not end the way we expect. Sometimes a star refuses to die. The last light of a zombie star. In the enormous scale of the universe, stars are constantly being created and destroyed. Across the Milky Way, clouds of gas collapse to form new suns, while others reach the final stages of their long and complex lives. Some fade quietly. Others end in violent explosions that briefly illuminate entire galaxies. For most stars, the story follows a predictable path: birth, life, and death. Yet the discovery of zombie stars has shown us that the universe does not always follow such clean endings. Sometimes the explosion that should destroy a star fails. Instead of disappearing completely, A remnant survives, a damaged stellar core, a quiet survivor of an event that should have ended everything. And for millions of years after that failed explosion, the zombie star continues drifting through space. But like all objects in the universe, zombie stars cannot exist forever. Their fate is ultimately shaped by the same forces that govern every star: gravity, energy, and time. If a zombie star remains within a binary system, its future can be especially dramatic. The companion star continues evolving, expanding slowly as it ages, its outer layers growing more fragile. Gravity from the zombie star begins pulling gas away from its companion. Material streams across space, forming a swirling accretion disk around the white dwarf remnant. This gas heats to extraordinary temperatures, millions of degrees, occasionally igniting in powerful nova eruptions. Each eruption blasts matter outward, but not always enough to stop the star from growing heavier. Slowly, almost imperceptibly, the zombie star increases its mass, year after year, century after century, until it approaches the critical boundary known as the Chandrasekhar limit. Once this limit is reached, the internal pressure inside the star becomes overwhelming. Electron degeneracy pressure can no longer support the star against gravity. The structure collapses inward, temperatures rise rapidly, and nuclear reactions ignite throughout the entire star. If this happens, the result will be catastrophic. A thermonuclear detonation sweeping across the star in seconds. This time, the explosion will not fail. The entire star will be consumed. Every atom ripped apart and hurled into space. The brightness of the explosion may briefly rival that of billions of suns. Astronomers observing from distant galaxies will see a brilliant flash of light. Another, Type 1, a supernova, the final destruction of a star that once refused to die. But not all zombie stars will experience such dramatic endings. Some may slowly lose mass through repeated nova eruptions, each eruption removing material that might otherwise push the star toward the Chandrasekhar limit. In these cases, the zombie star may stabilize, its mass remaining below the critical threshold, the eruptions becoming less frequent, the internal energy slowly fading. Over millions or even billions of years, the star may cool, its brightness gradually diminishing, eventually becoming a faint white dwarf drifting silently through space. At that point, nothing about the star's appearance would reveal its extraordinary past. It would look like countless other stellar remnants scattered across the galaxy. But hidden within its chemical structure would remain the evidence of its violent history. Elements forged during the failed explosion. Atoms created in nuclear reactions that once shook the star to its core. These atomic fingerprints are the only clues astronomers may have to reconstruct the star's ancient story. A story that began with a catastrophic supernova, a blast that nearly destroyed the star completely, yet somehow left behind a surviving remnant. The zombie star. Studying these remnants allows astronomers to explore one of the most fascinating questions in astrophysics. How do stars really die? The answer is far more complicated than scientists once believed. Stellar death is not always a single moment. Sometimes it is a long process, a struggle between gravity and nuclear energy, between destruction and survival. Zombie stars reveal that even the most powerful explosions can leave something behind, a core that continues evolving. a remnant that may explode again or slowly fade into darkness. Future telescopes will help astronomers uncover many more examples of these strange objects. New observatories will scan the sky for faint explosions and unusual stellar remnants. Powerful space telescopes will analyze the chemical fingerprints of distant stars. And massive surveys will track the motion of millions of stars across the Milky Way. Each new observation will help scientists identify more zombie stars hiding among the galaxy's enormous population. And with each discovery, our understanding of stellar evolution will grow, because the universe rarely follows the simplest path. Even the most violent events can have unexpected outcomes. A star can explode, its outer layers blasted across space, yet a portion of the star survives, a remnant drifting quietly through the galaxy. Neither fully alive nor completely gone. A cosmic survivor. Somewhere tonight, beyond the faint glow of the Milky Way visible in the night sky, zombie stars are continuing their strange existence. Some feeding on companion stars, some racing through the galaxy after ancient explosions, and some slowly cooling after surviving catastrophes that should have ended their lives. Their existence reminds us that the universe is far more mysterious than we once imagined. Even the death of a star can leave unfinished stories that continue unfolding for millions of years, stories written in nuclear fire and cosmic explosions, and sometimes in the silent glow of a star that once tried to die but refused. The cosmic cycle of death and survival. In the enormous history of the universe, stars have always followed a cycle. They are born within giant clouds of gas and dust. Gravity pulls this material together, pressure builds, temperatures rise, and eventually nuclear fusion ignites. A new star begins shining. For millions or even billions of years, that star produces light and energy. Inside its core, nuclear reactions transform simple elements like hydrogen into heavier ones such as helium, carbon, and oxygen. This fusion releases enormous energy. It is the force that allows a star to resist the crushing pull of gravity. But no star can burn forever. Eventually, the nuclear fuel inside the core begins to run out. When that happens, gravity begins to win the battle. The star changes. Its structure becomes unstable. And it begins its final transformation. For smaller stars, this ending is relatively calm. The star slowly expands into a red giant. Its outer layers drift away into space, leaving behind a white dwarf, a dense stellar remnant about the size of Earth. But for more massive stars, the ending is far more dramatic. When the core collapses, the star can explode in a supernova, an event so powerful it can briefly outshine an entire galaxy. These explosions scatter heavy elements across the universe, elements that later become part of new stars, planets, and even living organisms. In many ways, the death of stars is what makes life possible. Without ancient supernovae, the universe would contain only the simplest elements, hydrogen and helium. But the discovery of zombie stars has revealed that even stellar death does not always follow a simple path. Sometimes the explosion that should destroy a star is incomplete. Instead of vanishing, a portion of the star survives, a wounded remnant left drifting through space. For millions of years, that remnant continues evolving, its internal structure altered by the explosion, its chemical composition changed forever. In some cases, the zombie star remains inside a binary system, its gravity slowly pulling gas away from a nearby companion star. The gas spirals toward the white dwarf, heating as it forms an accretion disk, eventually falling onto the star's surface. This material can trigger nova eruptions, small thermonuclear explosions that briefly brighten the system. Yet the star itself remains intact, each eruption reshaping the remnant slightly, sometimes adding mass, sometimes removing it. Over time, this delicate balance determines the zombie star's ultimate fate. If the star continues gaining mass, it may approach the Chandrasekhar limit. When that limit is crossed, the internal pressure becomes overwhelming. Nuclear reactions ignite throughout the star, and a new thermonuclear explosion begins. This time, the explosion may succeed where the first one failed, destroying the star completely. But not every zombie star reaches that point. Some lose enough material during nova eruptions to prevent the catastrophic second explosion. Others drift alone through the galaxy, far away from any companion star that could feed them additional mass. These solitary remnants slowly cool, their internal energy fading. Over billions of years, they may eventually become faint stellar corpses, cold white dwarfs barely emitting any light at all. Yet even then, their strange history remains written within their atoms. The heavy elements created during their failed explosion remain locked inside the star, evidence of the violent processes that once nearly destroyed them. Astronomers studying these remnants can reconstruct that ancient event by analyzing the star's chemical composition and motion through space. Each zombie star, therefore, becomes a cosmic archive, a record of a failed stellar death. But perhaps the most remarkable lesson zombie stars teach us is how complex the universe truly is. For generations, scientists believed they had a clear understanding of how stars die. But nature often refuses to follow simple rules. Explosions can stall, burning flames can behave unpredictably, and stars can survive events that should have ended their existence. These discoveries remind us that the universe is still full of mysteries. Even phenomena we believed we understood may contain hidden complexities. Zombie stars represent one of those surprises, a reminder that cosmic evolution is not always straightforward. Sometimes it takes unexpected turns. A star explodes, but does not disappear. Instead, it continues drifting through the galaxy. A quiet survivor of cosmic violence. Somewhere in the Milky Way tonight, there are likely thousands of such stars, some hidden within binary systems, others racing through space after ancient explosions, and some slowly cooling in isolation. Their strange existence known only to the astronomers who search carefully through the sky. As telescopes become more powerful and observations more precise, scientists will continue uncovering these extraordinary remnants, each discovery revealing new details about the physics of stellar explosions. Each zombie star offering another clue about the chaotic forces shaping our universe. Because the universe is not simply a place of birth and destruction. It is a place of survival as well. Even after the most violent explosions imaginable, some stars remain, scarred, changed forever, but still shining faintly in the darkness of space, a silent testament to one of the strangest truths in astronomy. Sometimes, even death is not the end of a star's story. Echoes of an explosion, long after a supernova fades from view, the universe continues to carry the memory of the event. the brilliant flash of light disappears within weeks or months. The expanding debris slowly spreads across space, and eventually the explosion becomes just another quiet region of the galaxy. But for astronomers, the story of a stellar explosion never truly ends, because the aftermath continues unfolding for thousands, sometimes millions of years. Shockwaves from the blast sweep through interstellar space. Gas clouds are compressed, magnetic fields twist and stretch, and the debris left behind begins forming enormous glowing structures known as supernova remnants. These remnants are some of the most beautiful objects in the universe. Vast shells of expanding gas illuminated by radiation from the explosion. Filaments of glowing plasma stretch across light years of space. Elements created inside the dying star spread into the galaxy. Carbon, oxygen, iron, nickel. These materials eventually mix with other clouds of gas and dust, and in time, gravity may pull those clouds together again, forming new stars, new planetary systems, and perhaps even worlds capable of supporting life. In this way, the death of one star becomes the beginning of something new, a cycle of destruction and creation that has shaped the universe for billions of years. Yet zombie stars introduce a strange twist to this cosmic cycle, because when a star survives its own explosion, part of that cycle remains unfinished. The star that should have vanished continues existing, a remnant left behind after a catastrophic event, and its presence changes the environment around it. Inside many supernova remnants, astronomers search for the object that remains at the center. Sometimes they find a neutron star, sometimes a black hole, but occasionally they discover something unexpected. A surviving white dwarf, a zombie star. These remnants are often surrounded by expanding shells of gas from the original explosion. The debris cloud continues moving outward at enormous speeds, thousands of kilometers per second, but the zombie star remains near the center of the expanding remnant, a quiet survivor inside the glowing remains of its own destruction. Astronomers study these remnants carefully, because they reveal important details about how the explosion occurred. The shape of the expanding gas can show whether the explosion was symmetrical or uneven. The chemical composition of the debris reveals which nuclear reactions took place inside the star. And the surviving remnant itself provides clues about why the explosion failed to destroy the star completely. Some remnants show clear evidence of incomplete burning, regions where the nuclear reaction stopped before consuming the entire star. These patterns match the predictions of computer simulations describing deflagration explosions, slow burning waves moving through the star instead of violent detonations. Other remnants reveal strange asymmetries, large clumps of debris moving faster in one direction than another, evidence that the explosion was chaotic. These asymmetries may also explain why some zombie stars receive powerful kicks during the explosion, launching them across the galaxy at enormous speeds. The surrounding supernova remnant therefore becomes a kind of historical record, a snapshot of the explosion frozen in time. By studying its structure and motion, astronomers can reconstruct the events that occurred during the star's final moments, and in some cases, those reconstructions reveal that the explosion nearly destroyed the star, but not completely, leaving behind the strange survivor we now call a zombie star. These discoveries have forced scientists to rethink how supernova remnants evolve over time. In a typical supernova, the remnant gradually expands and fades as the energy of the explosion dissipates. Eventually, the gas mixes with the surrounding interstellar medium. The structure dissolves, and after tens of thousands of years, the explosion becomes almost impossible to detect. But when a zombie star survives, the remnant can evolve differently. Radiation from the surviving star may heat nearby gas. Occasional nova eruptions may inject new material into the expanding cloud. The remnant becomes a dynamic environment instead of a slowly fading one. Some zombie stars may even create complex structures inside the remnants of their original explosions. New shock waves, new shells of gas, new bursts of radiation. These interactions make the remnants far more complicated than astronomers once expected. But perhaps the most fascinating aspect of these remnants is what they reveal about time. Because when we observe a supernova remnant, we are seeing an event that occurred long ago. The light from that explosion traveled across space for years, centuries, or even millions of years before reaching our telescopes. In a sense, every supernova remnant is a message from the past, a signal telling us that somewhere in the galaxy long ago, a star exploded. And in rare cases, the message carries an even stranger detail. The star did not disappear. It survived, a remnant still shining faintly in the center of the expanding cloud, a survivor of cosmic violence. These observations remind us that the universe is constantly evolving. Events that seem instantaneous on human timescales can continue shaping the cosmos for thousands of years. Explosions create shock waves that travel across light years. Elements forged inside dying stars become the building blocks of future worlds. And sometimes, the star itself remains, a wounded survivor drifting through the debris of its own destruction. Somewhere among the countless glowing remnants scattered across the Milky Way, zombie stars continue their strange existence, silent witnesses to explosions that nearly ended their lives. And as astronomers continue exploring these remnants with increasingly powerful telescopes, they are uncovering more clues about the chaotic physics of stellar death. Each new remnant studied, each surviving star discovered, brings us closer to understanding one of the most remarkable phenomena in astrophysics, a star that exploded, yet somehow refused to disappear.